Hello everyone, welcome to part 27 module 2 computer networks. So far we were discussing about the max sublayer of Ethernet protocol, and when we look into that frame format, we were familiar with the fields like the preamble field, then the source and destination address field, followed by the type and length field, type or length field, depending on whether it is DIC standard or 802.3 standard. Next field is a data field, and in a typical Ethernet we have a restriction of 1500 byte as an upper limit for the data. I mean the content other than header, the data could be maximum 1500 byte. And why this limit? So this limit was chosen somewhat arbitrarily. At the time, the Ethernet standard was cast in stone, mostly based on the fact that a transceiver needs enough RAM to hold an entire frame, and RAM was expensive during the 1978. So that is the thing. But right now, this RAM is cheaper. You can accommodate a bigger size, of course. But when the time when this Ethernet standard come up, this RAM was expensive, and of course if the frame is of size bigger than this, then we need that much expensive RAM. More RAM is needed, which will make the entire system costly. So to avoid that, they have such a limit, and that is something arbitrarily chosen. Depending on the cost they can spend. So a larger upper limit means more RAM. A larger upper limit on the data size means more RAM, and hence more expensive transceiver, of course. So in addition to this maximum frame length, there is also a minimum frame length. So maximum, okay, it's by looking at the RAM requirement, we restrict it up to 1500. Now what about the minimum frame length? Will it be say 0 byte? So a field of 0 byte is sometimes useful, but it will cause a problem. So what is that problem? When it comes to collision, some kind of special collision signals will be generated, so to notify others about the presence of collision. And that time the frames were getting collided, and that will truncate the current frame, which means that some stray bits and pieces of frames may also appear on the cable. Now the media should distinguish between the original frame and the collision fragments. We can call it as collision fragments, the one which is resulted after a collision, and that is simply not at all a useful frame, right? So to distinguish a valid frame from how garbages were coming as part of the collision fragments. Sometimes they are also called rund frame. Somewhere I heard that name, rund frame, or garbage, or collision fragment. So the Ethernet requires a valid frame which is of size at least 64 byte. If it is the total size of the frame including header, if it is less than 64 byte, that means it's a garbage. So like that they will distinguish. And the 64 byte they are counting from the destination address to the checksum. You hope you remember that frame field, destination address, then source address, then type, length, then data, and checksum. Like that it is proceeding, right, including both. So together it is 64 byte. So if you look at the data part alone, this destination address is some 6 byte, then source address, destination address, both are 6, so totally 12 byte. Checksum is some 4 byte, right? So 12 plus 4, 16 byte. 2 byte length or type field. So totally 18 byte will be part of the header. Other than that data. So if you look at the data part alone, 64 minus 18, it will be 46, right? 46 bytes of data should be there, and you can see that if it is actual data is something less than 46 byte, we have the pad field of size 0 to 46 byte, and where we will pad zeros to make the frame of minimum size. If the actual frame is of less than 46 byte, you can zero pad it, and you can make it of minimum frame size. And why that minimum frame size? The reason one is to distinguish valid frame from the garbages or the rund frame. And there is one more reason for this requirement of 64 byte as the minimum frame length. So that is we are looking at the reason 2. So this is more important than the first reason. So the reason is like this. Another reason, or more important reason, for having a minimum frame length is to prevent a station from completing the transmission of a short frame before the first bit has been reached at the far end of the cable, where it may collide with another frame. the same concept we explained already. So whenever so from one point, if I started sending some information, say to this B, just before reaching B, it may collide with A signal, may collide with the B signal, and this collision will be informed back to A by this B or someone who is noticing collision, and this collision information should reach back. So totally some tau unit of time for the propagation of the data, and another tau unit of time for the collision signal to come back to the sender. So totally this 2 tau, right? So you have to ensure that your frame should be you should be able to send the frame means or the frame transmission time, the time taken to transmit your frame should be greater than or equal to this 2 tau, where tau is actually the propagation time, or you can denote by TP, propagation time, and transmission time, right? So how you will make this frame transmission time, and what is the formulation for frame transmission time? Length of the frame by bandwidth. And to increase this frame transmission time, you have to increase the size of the length of the frame. So there should be some minimum value for this length, and that minimum value is found to be 64 in a typical classic Ethernet, right? So that is the thing. So we get an idea. We will see that this problem is illustrated in the next slide. So it is something like this. From A, the same example I was trying to quote in the previous slide, started sending a frame say at time 0, and it reaches the total propagation time from here to here is some tau unit of time. So just before this reaching this destination, say tau minus epsilon. So epsilon is this small gap, okay? Before that, actually what happened is B also started sending the data, and the collision happened right at this point. So whenever there is collision, B will be notified first, right? Because B will be getting some signal of strength more than what is being sent by it. Collision signal will be added up, right? It will be high strength signal, so that will be received back by B. And what B will do, it will try to inform others about this collision. And naturally this A will also get to know about the fact. So how B will notify A about the collision by sending a special signal called a noise burst that will come back to A, maybe generated by B, right? And till it is coming back, A should keep sending the data. So forward we have a tau propagation time, and for this noise burst to come back, another tau unit of time, right? This noise burst to come back, another, so totally 2 tau, right? So the frame length of this A should be a value such that till this noise burst is coming back, A should keep sending the data, or the transmission time of frame transmission time of A should be greater than or equal to 2 tau, and this frame transmission time is nothing but length by bandwidth, greater than or equal to 2 tau, and bandwidth is fixed. Length of the frame, there should be some minimum value, so that is found to be 64 byte. We will see that. Explanation for the previous slide. At time 0, station A at one end of the network starts sending a frame. The propagation time be tau. Just before the frame reaches the other end, that is tau minus epsilon, the most distant station, say B, that also start transmitting. So when B detects it is receiving more power than it is being put out, more power in the sense because of the collision, it knows that the collision had occurred. So it aborts the transmission and generate a special noise burst which is of length 48 bit, and to warn other stations about this fact. So in other words, this B is trying to jam the entire ether, that media, to make sure the sender does not miss the collision. So somehow the sender should be known about the collision, then only sender can about its transmission, right? So to make it happen, it will try to send the special noise burst. It's otherwise called the jamming signal even, so because it is trying to jam the ether using that one, right? So jamming signal. And this is will come back by a time of 2 tau, because tau for actual propagation of the original frame, and another tau for the jamming signal or the noise burst to come back to the sender. So by this time the sender sees that noise burst, and it also aborts transmission. So after aborting, it will wait for random amount of time, and then after it will try again. Now, if the station tries to transmit a very short frame, maybe of length less than 64 byte, it is conceivable that a collision will occur, that it will understand by looking at the jamming signal, but the transmission may have completed before the noise burst get back to station, that is at a 2 so it will be confused whether it is its data that get collided or someone else's data, because when that collision signal come back, it's already sent the data, right? Such a situation should not come. So the sender will then incorrectly conclude that my frame has been successfully sent. Yes, a collision signal came back, but it is someone else's data get collided. It's not my data, right? So to prevent this from occurring, all the frames must take more than 2 time to send, so that the transmission is still taking place while the noise burst is coming back to the sender. So that is the criteria we need. So how we can ensure that the length of the frame is more than, transmission time is more than 2 otherwise the length of the frame should have some minimum value to ensure this criteria. So that is very important, right? So now how people come up with that 64 byte, so a kind of derivation is here. In a typical classic Ethernet, which is of 10 megabits per LAN, and when it comes to switched Ethernet and all, we don't have such collision problem, so it could have a different value. So the derivation is taken place for a typical classical Ethernet of 10 megabits per second speed. The maximum length of 2500 or 2.5 kilometers, something we already seen, right? 2.5 kilometer and 4 repeaters are supposed to be there as per 802.3 specification. Maximum length means between a sender and receiver, the maximum distance allowed is 2.5 kilometers and 4 repeaters also allowed at most. And in that case, the round trip time is calculated to be of 550 microseconds. So the maximum round trip time, considering this, this will be this is a length, right? So 2.5 kilometer length by, distance by velocity. You can find out the propagation time and 2 times of that, and that value is found to be some 50 microsecond of time. So if that is the case, the shortest allowed frame must be at least this long to transmit. So in a 10 megabits per second, what is the time taken to transmit a single bit, right? So how this calculation is done, in every second 10 mega bits were transmitted. So what is the time taken to transmit a single frame? It is 1 by 10 raised to 7 seconds. And what is that? It is nothing but, so you multiply and divide by 100, you will get 100 by 10 power 9. And 10 power 9 is actually 10 raised to minus 9 is nano, right? 100 nanosecond. So that is time taken for transmitting a single bit. Now we need the length of the frame should be in such a way that the time taken to transmit should be at least 50 microsecond. So to make it, we need a minimum 500 bits, right? So for 1 bit, 100 nanosecond of time. Then for 500 bits, how much time it will be taking? 500 into 100 nanosecond of time. So that will be 50 you take, and this nano and 10 raised to 3, that will be micro, right? So for 1 bit, the time taken is 100 nanosecond. 100 into 10 raised to minus 9 seconds. So for 500 bits, the time will be 500 into 100 into 10 power minus 9. So this is like this 50 you can take 50 into 10 raised to 3 into 10 raised to minus 9. So that will be 50 into 10 raised to minus 6. Minus 6 is nothing but micro. So we have to make the frame transition time to be 50 microsecond at least. You have to make the length of the frame to be 500 bits in a typical Ethernet with 10 megabits per second speed. So 500 bits you can round up to 512 bits, and that 512 bit is nothing but 64 bytes. So that is how they come up with the minimum size of 64 byte in a typical classic Ethernet. Okay. Now one more field, with that we will wind up this lecture, the checksum field. So data field is clear for you. So why there is a minimum frame size of 64 byte and a maximum frame size of 1500 byte. 1500 with some 36, 1536 actually the total value. The 36 is how you are getting that header and trailer together. Out of that 64 byte, 46 byte of data and 18 byte of header. Like that, that calculation is done. Now checksum field is a final one, which is a 32-bit CRC reminder will be kept in that field. CRC, there will be a generated polynomial, and depending on the type of the polynomial you are using, of course the CRC reminder is going to vary. It is an error detecting code, and that is used to determine the correct reception of its bits of the frame. It just does error detection, and if there is error detected, the particular frame will be dropped and the error will be notified so that the sender can retransmit it. So that about it. This CRC reminder calculation, everything we already covered in our data communication class. You can memorize it. Okay. Remember back. Thanks.